Assalamu alaikum dear students. I welcome you to the 9th lecture of probability and stochastic processes. In previous 8 lectures, we have covered many interesting applications of probability theory. In most of the cases that we discussed, all outcomes were equally likely. That is, the probability of picking an outcome from the sample space was same no matter what outcome was picked. Particularly in the last lecture, we took up a very interesting example where we took a unit interval and picked 2 points on the unit interval. When we picked 2 points, the unit interval was divided into 3 segments. The 2 points that we picked were picked independent of each other, and every point was equally likely to be picked. And once we had picked 2 points and had divided the line interval between 0 and 1 into 1, 2, and 3 line segments, we found probability of many interesting events, like what is the probability that the leftmost segment is the shortest, etc. As I said, in most of the cases that we have discussed so far, all outcomes were equally likely. In the absence of any other piece of information, it is natural to assume that all outcomes of the sample space are equally likely. But that is not always the case. Let's revisit some of the examples that we discussed. Let's start with the coin toss. If you take a coin, a fair coin, and toss it, there are 2 outcomes, head and tail, and they are both equally likely with probability of half. Similarly, if you roll a dice, there are 6 possible outcomes and all of them are equally likely. I hope you remember those pyramids or semi-cubes that my son made for a demonstration, I think 4 or 5 lectures ago. So if you take that semi-cube, which has 2 square sides and 4 rectangular sides, it's a cube squished a little, and if you roll that, then all outcomes are not equally likely. There are still 6 outcomes, 6 flat surfaces that will be on the top of the semi-cube when it comes to rest, but it is more likely that those square sides will be on top than the rectangular type, because it's more natural for this semi-cube to rest in this manner than in a standing manner. So in this case, there are 6 outcomes and they are not equally likely. Let's talk about another example that we discussed, the example of a sack with few red and few green balls. Suppose in the sack there are 6 red and 3 green balls, and you take out 2 balls, one after the other, without replacement. You take out a ball, keep it in your hand, take out another ball, and then you look at the colors of the 2 balls. So there are interesting events for this experiment. For example, what is the probability that both of the balls are of red color? Or what is the probability that both of the balls are of green color? If you find these probabilities based on what we have discussed in previous lectures, you will find out that if you perform this experiment without replacement, then there are 72 possible outcomes. These 72 outcomes are pairs of observation where first entry is the color of the first ball and the second entry is the color of the second ball. So what's the probability that both of these balls are red? Since there are 72 equally likely outcomes and there are 30 ways that we can have the 2 balls which are both red, so the probability of getting both balls red in color is 41.667%. Similarly, the probability of getting 2 green balls when there are 3 green and 6 red balls is 8.33%. And what's the probability that you get a red ball and a green ball? Irrespective of the order, you can get red first or you can get green first. Probability of that happening is 50%. So it looks like that this experiment has outcomes which are not equally likely. The probability of getting 2 green balls is small and probability of getting 2 red balls is higher. But we are talking about complex events here. The events that we are talking about are of special nature, which are picked from a sample space which is two-dimensional. It is a grid with 9 elements this way and 8 elements this way. There are 72 outcomes, and these outcomes are equally likely. But these outcomes are not red, green, green, red, or red, red. They are of this kind. They are red 1, green 1, or red 3, green 5, etc. Because there are 6 red balls and they are not the same. When you take out and it's not written that it's which ball, then it appears same to you, but they are not the same. So there are 6 red balls and you can call them R1, R2, R3, R4, R5 and R6. And there are 3 green balls, G1, G2 and G3. So getting a pair of a particular red and a particular green ball or other way around is same. So all 72 outcomes where 2 green balls differ from each other are same, but when you combine these outcomes into one event, one complex event, that we don't care if it is 3rd green ball or 5th green ball when we pick it, for us it's same, then we are combining many outcomes into events. And probabilities of different events can differ, even if the probability of all the outcomes on the sample space are same. So even if the probability of getting any outcome from the sample space is same, that is, all outcomes are equally likely, some events can have higher probability and some events can have lower probability. So in this case, the underlying experiment of getting a pair of observation of 2 balls is same, but the events have different probability. Let's talk about another interesting example. Suppose you live in a big city, and in this city there are restaurants of different kind, indigenous, local type, as well as foreign franchises, franchises of international food chains of fast food type restaurants. So if you stand outside such an international franchise of fast food restaurants and you count the number of people that go inside that restaurant in a, say, 10-minute interval, then you can observe different number of people going in the restaurant. So what's the probability that 10 people will go in a given 10-minute interval? What's the probability that 100 people will go? What's the probability that 0 people will go in a given 10-minute interval? Whatever those probabilities, it is obvious that these probabilities are not equal. Probability of nobody going versus probability of, say, 25 people going versus probability of, say, 1,000 people going. They are all different. So let's see what these probabilities could be. Suppose everything is normal, well, as normal as it gets in this part of the world, and our population is not trying to torch and burn everything which looks foreign and vulnerable, then there will be people who are going to that restaurant. So probability of 0 people going inside that restaurant is pretty small. Similarly, probability of 1,000 people going inside the restaurant in a given 10-minute interval is also small, based on the size of the restaurant and the location where it is located. It's highly unlikely that in a given 10-minute interval, thousands of people will visit that. But probability of 20 or 25 people or 30 people going into that restaurant in 10-minute interval is reasonably a large number, greater than 0. So is this random experiment of observing the number of people going inside a restaurant in a given 10-minute interval has equally likely outcomes or outcomes which are not equally likely? It appears that this observation of counting the number of people in 10-minute interval has outcomes which are not equally likely. But it's possible that there is some underlying much simpler experiment, and this observation of number of customers going in the restaurant is a complex event. It's not the elementary outcome of that underlying complex experiment. We'll see that in a while. But The summary is that sometimes we encounter situations where all possible outcomes are equally likely, and sometimes all possible elementary outcomes are not equally likely. And even for the cases where all elementary outcomes are equally likely, we can define events with different probabilities. So those complex events may have different probabilities even though the underlying experiment has equally likely outcomes. When we do have to work with situations where outcomes are not equally likely, then we have a formal framework for doing that, and it is called random variables. When you are dealing with random variables, you are not dealing directly with the outcomes of the random experiment. Instead, you take the outcome and transform it to a number on real line. So when you are dealing with random variables, no matter what the underlying sample space is, you are only dealing with points on real line from -infinity to infinity. So to assign probability to event, you assign probability to this point on real line, and this point indirectly refers to some outcome. It may refer to an elementary outcome, or this point may refer to a complex event, but we don't care. We forget about the sample space and work with the real line. So random variable is a mapping which maps the sample space to points on a real line, and then we take this real line as domain of our probability function. We take points on this real line and assign to them values between 0 and 1. We say the probability of this mapped position or this random variable getting this particular value is this. Any number between 0 and 1, say 0.2. So random variable is a mapping, and when we say this random variable takes a value of 0.2 with probability 0.1, then we are saying that all those outcomes, could be one, could be many, all those outcomes which get mapped to this point 0.2 have a probability of 0.1. This will be clear if we take a concrete example. It is presented in this slide. Let's have a look at this. Suppose you take two fair dice and roll them, and we have discussed it already that the sample space is a two-dimensional grid, 6 by 6 grid, and the outcomes are pairs of observation where first entry is the number of dots on the first dice and the second entry is the number of dots on the second dice. But we are not interested in this detailed information. We want to deal with something simpler, something transformed, a random variable which maps these elementary outcomes, pairs of observation, into numbers on real line. Let's take this mapping to be sum of all the dots. So if you roll two dice, count number of dots on the top face of one dice, count number of dots on the other dice, add them together, you get a number, an integer number. So this integer number is of interest to you. And then you talk about probability of this experiment, mapping the sum to a number, and probability of that number indirectly telling you what was the event that generated that sum. So if you analyze this problem further, as it is done in this slide, you will see that there are many outcomes that this random variable can have. The sum of two dice can have a minimum value of 2 and a maximum value of 12. 2 happens when both dice show up 1 on the top surface, and 12 happens when both dice show 6. So the range of outcomes of this random variable is 2 to 12, and they are integer values. So what is the probability of this random variable having a value 2? Then you should look at the sample space, and sample space has only one elementary outcome, that is 1, 1, that is both dice show 1, and the probability of that elementary outcome in the sample space is just 1 over 36. What about other points that random variable attains? It is clear that probability of random variable attaining a value of 12 is also 1 over 36, because this is attained by just one elementary outcome, 6, 6. Let's talk about probability of this random variable attaining a value of 4. The sum is 4. This sum can be obtained by many elementary outcomes. For example, the first dice can show 2, the other dice can show 2 also. Sum is 4. First can have 3, the second can have 1, or first can have 1 and second can have 3. So there are 3 elementary outcomes, 2, 2, 3, 1 and 1, 3, which give a sum of 4. So if you are talking about probability of random variable getting a value 4, you are indirectly talking about 3 elementary outcomes. So probability of this random variable, which is sum of the numbers you have on 2 dice, getting a value 4 is 3 over 36. And the maximum probability occurs for a sum of 7. The probability of this random variable having a value of 7 is 6 over 36, and you can certainly count all the elementary outcomes which generate a sum of 7. There are 6 of them. When you are dealing with random variables or a mapped outcomes from sample space to real line, then you are dealing with same problem as we assign the probabilities to events. Now we assign probabilities to these numbers. We assign probabilities to events like this, that random variable will have this much value, and this indirectly relates to events. So when you have to assign probabilities to numbers on real line, then you are using a probability function which assigns numbers to these points which are between 0 and 1, just like the probabilities assigned to events in signal algebras. So when you have a real line and there are points which are the values attained by random variables or possible outcomes of the experiment mapped to this real line, and then you assign probabilities to these numbers, you have what we call a probability mass function. It's also called probability density function, but for these cases we'll refer it with probability mass function. So what is probability mass function? It is a function where you assign a number between 0 and 1 to points on real line. And the next slide shows one example of such a probability mass function. You will see in this slide that probability mass function is assigned to real line, but only at values of 2, 3, 4 up till 12. For these integer valued locations, we have assigned different values of probability, which are shown as 1 over 36, 2 over 36, all the way up to 6 over 36, and then they go down again to 1 over 36. I hope you have realized that this is exactly the probability mass function of the last example that we discussed, that is rolling of 2 dice and then observing the sum of number of dots on the 2 dice. So this probability mass function is defined for real values of 2 to 12, integer valued, and the probabilities that we assign are the probabilities of all the events, elementary or complex, that generate these numbers between 2 and 12 when we take sum of number of dots. We can answer many questions about this random experiment and about this random variable by looking carefully at probability mass function. For example, we can ask, what is the probability that sum of dots on 2 dice will be equal to 10? From this sample space, this refers to a complex event where there are 3 equally likely pairs of observations which give a sum of 10. Hence, probability of a random variable attaining a value of 10 is 3 over 36, and this is clearly seen in the slide. We can ask even more complex questions. For example, what is the probability that the sum is a number less than 7? Even if we consider these outcomes of random variable as elementary outcomes, even though they refer to complex events in sample space, this particular event, that is, what is the sum being less than 7, contains multiple outcomes in the random variable. Now we are talking about all those outcomes which give a sum of 2 or 3 or 4 or 5 or 6. So there are a bunch of outcomes in the original sample space which generate a sum which is less than 7. Actually, you don't have to worry about those outcomes in the sample space. Just look at the probability mass function and see all those values that the random variable attains which give a sum of 7 less than 7, not 7. So what are these outcomes? 2, 3, 4, 5 and 6. And what are the probabilities of random variable attaining these values? They are 1 by 6, 2 by 6, 3 by 6, 4 by 6 and 5 by 6. And if you sum all these probabilities, you get 15 over 36. So probability of performing that underlying experiment where 2 dice are rolled and then summing the number of dots on the 2 dice and generating a random variable which is sum of the number of dots on 2 dice and getting a number less than 7, 6, 5, 4, 3, 2 is equal to 15 over 36, and you can answer this question readily by just looking at probability mass function. Actually, if you are given a probability mass function, you don't have to refer to the underlying experiment and underlying sample space. You can work directly with the probability mass function and ask interesting questions and get meaningful answers about the probabilistic behavior of this random variable. Since you are not interested in the actual outcomes, you can answer questions related to the behavior of this random variable which is mapping from sample space to real line. Let's look at another example of random variable which is generated through roll of dice. This example is of a gambling game which is played in Western countries where infidels have legalized gambling. In this country, in this Islamic Republic of Pakistan, we do not engage in gambling and other sins. But for the sake of learning probability theory, we'll talk about this example. Suppose somebody rolls 3 dice and you place a bet. The person who is rolling 3 dice could be employee of a gambling house. So he rolls 3 dice and you place a bet. Your bet is $1. This is how you win. If you call a number, when you place a bet, you call a number. Any number between 1 and 6. Say you have called 4. So when that person rolls 3 dice and 4 appears on all 3 dice, you win $3. If your called number 4 appears on 2 out of the 3 dice, you win $2. And if it appears any one of the 3 dice, you win $1. And if your called number does not appear on any of the 3 dice, you lose your bet of $1. So this random experiment is a joint experiment of 3 dice getting rolled. The sample space has outcomes which are vectors of length 3. It is observation 1, observation 2, observation 3. Each observation is a number between 1 and 6. The total sample space contains 216 outcomes and they are all equally likely. But you are not interested in this large collection of outcomes. You are interested in your gain or loss. So you are interested in a random variable defined on this underlying sample space of 216 outcomes, and your random variable can attain 4 values. -1, that is your loss, 1, which is your small profit, 2, or the jackpot of 3. So this random variable has only 4 outcomes, 4 values that it can attain, and now we have to assign probabilities to these outcomes. Let's start with the outcome that all 3 dice will have your called number, say 4. This is only possible if all 3 dice have 4 on top and there is only one outcome in that underlying space which generates this outcome. So the probability of you winning $3 is 1 over 216, reciprocal of 216, a pretty small number. And what is the probability of you winning $2? It turns out that it is 15 over 216. And what is the probability of you winning $1? It is 75 over 216. And probability of you losing your bet is 125 over 216, much bigger than half. So probability of anybody playing gambling games like this and winning something is pretty small, and probability of losing your bet is large. So moral of the story, don't gamble. Let's look at another random variable, very interesting random variable. It's called Bernoulli random variable or binomial random variable. It has a name because it arises in many real life applications. Suppose you start with a simple experiment with just two outcomes, like a coin toss. But it doesn't have to be coin toss, it can be something else. And on this underlying simple experiment with two outcomes, you define two events. One is success, one is failure. So there are two outcomes. You call one outcome success, the other failure. You can even assign numbers to them, like success is 1 and failure is 0. You take this experiment and perform this experiment number of times, say n times. When you perform this simple experiment n times, then sometimes there will be success, sometimes it will be failure. And then you count the number of successes. So you start with a simple experiment, perform it n times, and these n repetitions of experiment are independent of each other. And out of these n outcomes of simple experiment, you count the number of successes. As you can see, the number of successes, if a simple experiment is performed n times, could be 0 or n or any integer in between. So what's the probability that you perform such an experiment n times and you don't succeed at all? Like every time failure occurs, every time zero valued outcome occurs, every time tail occurs. And what's the probability that you succeed every time or something in between? This can be easily found out if you look at the underlying sample space of these n repetitions. If you perform this experiment twice, then there are 4 outcomes, 4 pairs of 2 values. For example, in case of coin toss, they are head-head, head-tail, tail-head, and tail-tail. And if you perform a simple experiment like coin toss or any other experiment with just 2 outcomes n times, then the outcomes are vectors of length n. There are n observations, and there are a total of 2 raised to power n outcomes if experiment is performed n times. So on this big sample space, you count the number of successes. If you have represented those outcomes with 0 and 1, then those outcomes are length n binary words, 0, 1, 1, 0, 0, etc. So there are length n binary words. So what is the number of bits which are 1 in a length n randomly chosen word, binary word? So these are the kind of experiments that binomial distribution or Bernoulli distribution handles. So let's make this experiment more general. In coin toss, the outcomes are equal. They are equally likely. Head and tail are equally likely. Probabilities are 0.5. Let's remove this restriction. Let's say you have 2 outcomes. You have called one success, other failure. You assign probability to this success as p, where p, small p, is a number between 0 and 1. If you assign probability of p to success, then probability of failure is 1 minus p. So what's the probability that you perform this experiment n times and there are a certain number of successes? And these number of successes can be represented by a symbol k. So you perform experiment n times, and what's the probability that there are k successes, where k is 0, 1, 2, all the way up to n. It's not very difficult to find this probability if you think carefully about those random experiments, the repetitions and repetitions being independent of each other. Then you can figure out that for a certain outcome, which is length n vector, and it has k successes, there are k success outcomes and capital N minus k failure outcomes. And what is the joint probability of this outcome? This complex outcome, which is the product of all those smaller outcomes of individual repetitions. So if individual repetitions are independent, then the probability of this combined event is multiplication of probabilities of individual outcomes. That is, if you are looking at an outcome which has k successes and capital N minus k failures, then probability of just that outcome is p raised to power k and 1 minus p raised to power n minus k. So that is the probability of individual such length n vector which has k successes and n minus k failures. But it's possible that there are multiple outcomes like that which have k successes and n minus k failures. Let's take a few examples. How many outcomes are there which have no success, all failures? This is just one, where the failure occurs every time. So what's the probability of you having no success after trying some experiment n times? It is 1 minus p raised to power n. And similarly, what's the probability that you perform some experiment n times and succeed every time? It is p raised to power n. But there are other outcomes. For example, if you perform experiment n times, then what is the probability that 4 successes are encountered? Then there are multiple outcomes which give you 4 successes. If you think of length n binary words, then if length n is larger than 4, then there are many ways you can have 4 1 bits distributed in this. Consider it like this. There are capital N number of chairs. There are 4 people standing here, and you want to seat them on those chairs. They can go and sit. But once they have seated themselves, if you switch 2 people, you get the same arrangement as far as appearance of those binary words where zeros and ones are concerned, or appearance of the chairs where empty and occupied chair is concerned. So when you are trying to find how many ways you can have 4 1 bits in length n, you are doing combination. The number of ways you can have 4 ones in length n binary word is n choose k, which is n factorial divided by k factorial divided by n minus k factorial. So you use this. This is the number of outcomes which generate k successes. So this is the number of outcomes, and each outcome length n word with k successes have a probability of p raised to power k, 1 minus p raised to power n minus k. You combine these all things and you get the binomial distribution. The binomial distribution has many interesting applications. Let's revisit an experiment and see how binomial distribution can be used to analyze that. The experiment I'm referring to is that experiment where we stood outside an international fast food franchise and counted number of people going in a 10-minute interval. Actually, this observation is a complex event, and it builds on top of a much simpler event, that is, what is the probability that one person enters this franchise in a very short interval. To go further, we have to make certain assumptions. First, that this interval is so small that only one person can enter. So either one person enters or nobody enters. In this interval, 2, 3, 4, 5 people cannot enter. The interval is very small. The other is the actual process of entering inside this restaurant. It is instantaneous. It's not that person is walking slowly and is taking 10 seconds to enter. It happens suddenly. So either a person enters in a given small time interval or it does not enter. So let's assume success to be that a person did enter in a small time interval, and failure that person did not enter. So P, the probability of a person entering in a small interval, is something between 0 and 1, and it does not have to be 0.5 like the case of coin toss. Under these assumptions, let's divide the 10-minute interval into smaller intervals, small enough so that only one person enters. I'm going to take that small interval to be 5 seconds. You can certainly argue that 5 seconds is too long, 4 or 5 people can enter if they want to, but I'm going to restrict myself to 5 seconds. Why? The reason will be clear by the end of this discussion of binomial distribution and its application to number of people entering restaurant. So in a 5-second interval, either one person enters or nobody enters, and we take a 10-minute interval and divide it into 5-second intervals, and we have 120 such intervals. So we repeat that experiment of observing a 5-second interval and seeing if a person enters or not 120 times. So capital N is 120. This is binomial distribution, provided that persons entering are independent of each other. They are doing it independently of each other. Even though this is not true, because people go in large groups of friends or all families, but we will assume for the sake of simplicity that a person enters and he or she enters independently of the previous people who did enter or the people who are going to enter after him or her. So you perform this simple experiment 120 times and you meet success or failure sometime out of these 120 times. So what is the value, the range of values that this random variable, which is number of people entering the restaurant in 10 minutes, it is 0, 1, 2, all the way to 120. By taking this 5-second interval and assuming binomial distribution, we have restricted our range from 0 to 120. This is large enough, I guess. So how do you find the probability of a certain number of people entering this restaurant using binomial distribution? You apply the binomial formula, and if you apply that, you will see that probability of 0% entering is very small. Similarly, probability of 120 people entering is also very small, and people enter according to this distribution in the range of 5 to 40, and probability of entering 5 people is small, probability of 40 people entering is also small. The largest probability occurs for 24. That is, under these simplifying assumptions, probability of 24 people entering the restaurant in given 10-second interval is 24 if P is equal to 0.2. If you take a certain other value of P, then the maximum value will occur at some other point. So this value of P depends how big an interval you have chosen and how popular this restaurant is. I have this probability mass function shown on this slide. And if you look at this slide, you will see that I have only shown a portion of the range that we have considered. I have only shown from 0 to 50, even though all possible 0 to 120 could have been shown. But probability of 50 or more people entering is essentially 0. So I have restricted the view from 0 to 50. And it's clear that maximum probability is for 24 people to enter. I told you that I intentionally divided this 10-minute interval into 120 slots for 5 seconds each. The reason is that when you are finding the probability mass function values for different values of random variable, you have to do many complex computations. You have to take factorials, and you have to raise P with K and raise 1 minus P with N minus K. For numerical computation of these values, you have to restrict yourself to a reasonable range. I had to use MATLAB to generate this slide, and I could not have used 1200 as a number that I can feed in the factorial. It's simply not possible because it causes overflow of the data structures used to represent these floating point numbers. Similarly, when I take P to be a small number, for example 0.01, and I raise it, say, with a power of 30, then the resulting number is so small that it causes underflow. All the bits become 0, and I cannot keep track of these computations. So I have to restrict myself to reasonable range. The next distribution, which takes care of these extreme nature of binomial distribution cases, is called Poisson distribution. The Poisson distribution has its own applications, but it started as approximation of those cases of Bernoulli distribution where capital N was very large and or the P was very small or P was very close to 1. In both cases, when P is very close to 1, 1 minus P is very small and the problem is the same. So for these cases, when capital N is very large and P is very small, you have to use Poisson distribution, which is a manageable and trackable approximation of binomial distribution for these extreme cases. As you can see from this slide, that Poisson distribution has a formula which involves exponentials and factorials. And factorial is for only those numbers which represent the number of successes in such trials. So the expression is there, you can see on the slide, and I have used this expression to find the Poisson distribution for this experiment that we were talking about, that is standing outside the door of an international fast food franchise and counting the number of people going in. So for this case, I have decided to take n to be 1200. And if I take n to be 1200, then I have divided this 10-minute interval into 0.5 second intervals. I hope this is small enough and only one person can enter. If you want to, you can divide this 10-minute interval into 12,000, and then each small interval will be 0.05 second. And you can imagine the probability of success, that is a person entering in a given 0.05 second, will be very small. So if you take these numbers, capital N to be a large value, P to be a small value, and then you multiply the two, you get a parameter of Poisson distribution, which is lambda. So lambda is the large number n multiplied by the small probability P. And the trick is this number, capital N into P, should not be very far away from unity. It can be 1.1, 2, 5, 10, 20, something in the range, but not a huge number like thousands and not a very small number. And in our case, if we had used P to be 0.2 when the interval was 5 seconds, and then interval was reduced by 10 to 0.5, and then this P was reduced to 0.02, or the interval could be reduced to 0.05 and this to 0.02. In any case, when you multiply the two, capital N, the number of intervals, small intervals, and this small p, you get your lambda to be 24. So I have used a lambda of 24, and I have used the expression on this slide to plot the Poisson distribution for this type of random experiment. And remember, this Poisson distribution is defined for every positive integral value that is there, 0, 1, 2, all the way to positive infinity. But based on number of n and number p or the lambda, there is only a certain range where significantly large probabilities are observed. And in this case, that number again is between 10 and 40. So this distribution is an approximation of binomial distribution for very large n, that is very small time interval, and very small p, probability of success, that is probability of one person entering the restaurant in that given small interval. Probability mass function for these type of random variables tells the random variable can attain this value with this much probability. There is another function defined on real line related to any given random variable, which also carries very nice kind of information. It is called cumulative distribution function. Once you have transformed the sample space to real line, you have taken outcomes and mapped to values on real lines, then you define events on this real line, on this random variable, and these events are of this type, that what is the probability that this random variable can attain a value from minus infinity to a certain point, say t. So you pick a certain point t, make it a parameter, and then you find probability of all the things to minus infinity from that t, including that t, and going all the way to minus infinity. All the outcomes are combined. The outcomes are the values of random variable. So what's the probability that a given random variable takes a value, any value from minus infinity to a certain value t. This event, this probability is called cumulative distribution function of this random variable at point t. So this is a function of t where t is a point on real line, and as t changes, the number of values that a random variable can attain also are included and the probability changes. This cumulative distribution function has very interesting properties. For example, if we take our t to be a very large negative number, say towards minus infinity, very big but negative number, then the number of outcomes of random variable in that range from that number to infinity are small. So probability of that event, that is random variable, will be between minus infinity to that large negative number will be small. So the CDF for a very large negative number will be a small number. As t keeps increasing, more and more outcomes of the random variable are part of the event, and the probability of these events becomes bigger and bigger, and the CDF becomes bigger and bigger as a function of t as t goes from minus infinity to infinity. So if you pick your t to be a very large positive number, very large, then all the outcomes from this positive large number to minus infinity, they will constitute the event whose probability is the value of CDF at that positive large number. So value of CDF at a positive large number is large, and as this number approaches plus infinity, this CDF approaches 1. So in the limit, the CDF for a random variable is 0 for t minus infinity and 1 for t positive infinity. And there is way you can go from probability mass function to cumulative distribution function, and this is shown in the slide where it says that if you want to find the probability mass function from cumulative distribution function at a certain point t, you subtract the value of CDF at that point, and from that you subtract a point which approaches this. This concept is clearly discussed in your class handouts and any textbook, and this is an elementary concept and you should think about it and master it. To summarize what we have discussed today, we have talked about random variables. Random variables are intermediary representation of the random phenomena where we take these outcomes in the experiment in the sample space and map them to points on real line. And when you have mapped points to real line, then you assign probabilities to these mapped values, and these mapped values are random variable. So probability of this mapped value attaining a certain value, that is probability of random variable being equal to this value, is equal to probability of all the outcomes that get mapped to this. There are interesting points about random variables and their probability mass functions. One is that if you add all the values of probability mass function, you will get 1. Think about it. In next lecture, we are going to continue to talk about probability mass function, cumulative distribution function, and other interesting properties of random variable. So far, we are discussing discrete random variables, and from next time onward, we'll expand our horizon and include continuous random variables. Till then, I wish you the best. Khuda Hafiz.